At this very moment, more than 14 billion miles from Earth, a machine built in the 1970s is still whispering to us. It is moving through a darkness no human being has ever seen. Beyond the planets, beyond the Kuiper belt, beyond the protective bubble carved out by our sun. Out there, sunlight is faint, reduced to a bright star among countless others. Temperatures hover near absolute zero. Charged particles drift like invisible tides. And in that silent ocean between the stars, Voyager is still listening. For decades, we imagined the solar system as something solid and defined, a neat arrangement of planets orbiting a powerful star. But the truth is stranger. The solar system does not end with Pluto. It does not end with the last icy rock. It fades into a boundary region where the sun's influence weakens and interstellar space begins to push back. A cosmic shoreline. A frontier shaped not by rock or gravity alone, but by magnetism, plasma, and invisible radiation. In 2012, Voyager 1 crossed that boundary. It slipped beyond the heliosphere, the vast magnetic bubble inflated by our sun. For the first time in human history, an object made by us entered interstellar space. And what it detected there was not emptiness. Instead, Voyager found a region more dynamic, more structured, and more mysterious than scientists expected. It detected the sound of interstellar space. It measured sudden changes in radiation. It crossed invisible shockwaves that ripple through the galaxy. It revealed that the edge of our solar system is not a clean line, but a turbulent, shifting boundary between two immense forces. This is not just a story about a spacecraft. It is a story about the limits of human reach, about a signal that has traveled billions of miles to tell us what lies beyond our sun's protection, and about a frontier that redefines where home truly ends. Because when Voyager reached the edge of our solar system, it did not find silence. It found a boundary alive with energy, and in that discovery, our understanding of the universe changed forever. If you're fascinated by the quiet, hidden mechanics of the cosmos, subscribe to The Boring Universe. Like this video to support deep science storytelling, and leave a comment telling us which part of the country you're watching from. Your curiosity fuels this journey beyond the known. For most of human history, the solar system ended at Saturn, then it extended to Uranus, then Neptune, then Pluto. Each time we discovered a new world, our boundaries shifted outward. But these were psychological borders, defined by visibility and technology. The true edge of the solar system is not marked by a planet. It is marked by the sun itself. The sun is not just a glowing sphere of nuclear fusion. It is a generator of wind. From its outer atmosphere, a continuous stream of charged particles flows outward in all directions. This solar wind is composed primarily of electrons and protons, traveling at speeds of hundreds of miles per second. It carries with it the sun's magnetic field, stretching that magnetic influence outward into space. As the solar wind expands, it forms a vast bubble in the interstellar medium. This bubble is known as the heliosphere. Inside it, the sun dominates. Its magnetic field guides charged particles. Its radiation shapes the environment. Its wind pushes outward against the thin gas that fills the Milky Way. The heliosphere is not spherical. It is shaped by motion. As our solar system orbits the center of the galaxy at nearly 500,000 miles per hour, it moves through interstellar space like a ship through water. The heliosphere becomes compressed in the direction of motion and stretched out behind us, forming something like a cosmic wake. At its outer limits, the solar wind begins to slow. Far from the sun, the wind has traveled so long and so far that it encounters resistance from the interstellar medium. The pressure of the surrounding galaxy pushes back. This creates a boundary region known as the termination shock. The termination shock is where the solar wind abruptly slows from supersonic speeds to subsonic speeds. It is not a physical wall. It is a shockwave, similar in principle to the sonic boom created by a jet breaking the sound barrier. Here particles heat up, magnetic fields tangle, turbulence increases. Beyond the termination shock lies the heliosheath, a vast, turbulent region where slowed solar wind piles up against the interstellar medium. It is a mixing zone, where particles from the sun and particles from the galaxy interact in complex ways, and beyond the heliosheath lies the heliopause. The heliopause is the true boundary. It is the point where the outward pressure of the solar wind balances the inward pressure of interstellar space. On one side, particles dominated by the sun. On the other, particles shaped by distant stars and ancient supernovae. For decades, this boundary was theoretical. We could model it, we could simulate it, but we had never touched it. That changed because of a mission launched in 1977. Voyager 1 and Voyager 2 were designed during the Cold War at a time when computing power was measured in kilobytes. Their primary mission was to explore the outer planets. Using a rare planetary alignment that occurs once every 176 years, the spacecraft would swing past Jupiter, Saturn, Uranus, and Neptune, gaining speed through gravitational assists. They were never meant to reach interstellar space. Their power sources were designed to last a few decades. Their instruments were built with the expectation that planetary encounters would be the climax. Yet after completing their planetary tours, both spacecraft continued outward. As they left the giant planets behind, Voyager 1 headed north of the ecliptic plane. Voyager 2 traveled south. They were placed on escape trajectories, moving fast enough to eventually leave the Sun's gravitational influence. As the years passed, the signals from Voyager grew fainter. Radio transmissions traveling at the speed of light took hours to reach Earth. The Deep Space Network, a global array of enormous antennas in California, Spain, and Australia, strained to detect whispers measured in billionths of a watt. But the spacecraft kept working. By the early 2000s, Voyager 1 was approaching the termination shock. Scientists expected to see a gradual transition, a smooth decrease in solar wind speed. Instead, the data showed something more complicated. In 2004, Voyager 1 crossed the termination shock at a distance of about 94 astronomical units from the Sun. An astronomical unit is the average distance between Earth and the Sun, about 93 million miles. This meant Voyager was nearly 9 billion miles away. The crossing was not clean. Instruments detected sudden increases in energetic particles. The magnetic field grew more chaotic. The spacecraft entered the heliosheath, a region far more turbulent than models had predicted. Inside the heliosheath, the solar wind no longer raced outward freely. It slowed and compressed. Magnetic field lines twisted and folded. High-energy particles from outside the solar system began to leak inward in greater numbers. These incoming particles are known as galactic cosmic rays. They are accelerated by violent astrophysical events such as supernova explosions. They travel across the galaxy at nearly the speed of light. Inside the heliosphere, the Sun's magnetic field deflects many of them. But as Voyager approached the Heliopause, it detected increasing levels of these cosmic rays. At the same time, particles originating from the Sun began to decrease. Scientists realized they were witnessing a competition between two domains. The Sun's influence was weakening. The galaxy's influence was strengthening. But the most dramatic moment came in August 2012. Voyager 1's instruments recorded a sudden, sustained increase in galactic cosmic rays. At the same time, particles associated with the solar wind dropped sharply. The change was abrupt, occurring over a relatively short distance. It was as if the spacecraft had crossed an invisible border. Yet there was confusion. The magnetic field direction did not change as dramatically as some models predicted. Researchers debated whether Voyager had truly entered interstellar space or was inside a transitional layer. The answer came from an unexpected source. Voyager carries a plasma wave instrument capable of detecting oscillations in charged particles. When a shock wave from a solar eruption traveled outward and passed by Voyager in 2013, it caused the surrounding plasma to vibrate. By measuring the frequency of these oscillations, scientists could determine the density of the plasma around the spacecraft. The density was much higher than expected for the heliosheath. It matched predictions for interstellar space. Voyager 1 was no longer inside the Sun's bubble. It had crossed the Heliopause. For the first time, humanity had direct measurements of the interstellar medium. And what Voyager detected there reshaped our understanding of the solar system's boundary. The region just beyond the Heliopause was not empty. It was filled with plasma, thin but measurable. The temperature was surprisingly high, reaching tens of thousands of degrees Kelvin, though the density was so low that it would feel like a near-perfect vacuum. Magnetic fields threaded through this space, shaped not by the Sun but by the galaxy. Voyager found that the magnetic field direction just outside the heliopause was similar to that inside, suggesting that the boundary is more porous and complex than a simple dividing line. The heliopause itself appears to ripple and shift in response to solar activity. When the Sun experiences periods of high activity, its wind strengthens, pushing the boundary outward. During quieter periods, the heliosphere contracts. This means that the edge of our solar system is dynamic. It breathes with the solar cycle. Voyager 2 confirmed and expanded this picture in 2018 when it crossed the heliopause in a different region of space. Its instruments were still fully functional, allowing direct measurements of plasma flow. Voyager 2 observed a similar pattern, a drop in solar wind particles, a rise in galactic cosmic rays, and a sharp boundary marking the transition. Together, the two spacecraft revealed that the heliosphere is not symmetrical. The distances to the Heliopause differed in the north and south directions. The shape of our solar system's protective bubble is distorted by external magnetic fields and interstellar pressure. What Voyager detected at the edge of our solar system was not simply the end of something. It was the beginning of direct contact with the galaxy beyond. Inside the heliosphere, Earth and the other planets are shielded from a significant portion of galactic cosmic radiation. This shielding plays a role in the long-term radiation environment of our planet. It influences atmospheric chemistry and potentially even biological evolution over geological timescales. Beyond the heliopause, that shield weakens dramatically. Voyager's data has allowed scientists to refine models of how cosmic rays propagate through the galaxy. It has provided ground truth measurements that anchor decades of theoretical work. It has revealed that the boundary between stellar systems is not sharp but layered and active. Perhaps most profoundly, Voyager has shown that our solar system is not isolated. It is embedded in a local interstellar cloud, a region of slightly denser gas and dust through which our sun is currently traveling. The properties of this cloud influence the shape and size of the heliosphere. In time, as the sun moves through different regions of the galaxy, the heliosphere may change in size and strength. The cosmic environment of Earth is not fixed. It evolves on timescales of tens of thousands to millions of years. Voyager's journey has turned the abstract concept of interstellar space into something tangible, a measurable environment with density, temperature, and magnetic structure. Yet the spacecraft continues outward. Its power supply, based on radioactive decay, is slowly diminishing. Instruments are being turned off one by one to conserve energy. Eventually, Voyager will fall silent. Its last signal will fade into the background noise of the cosmos. But even after its voice disappears, Voyager will continue traveling. In about 40,000 years, it will pass near another star. Long after humanity's current civilizations have changed beyond recognition, the spacecraft will still carry its golden record, a time capsule of sounds and images from Earth. At the edge of our solar system, Voyager detected more than plasma and radiation. It detected a threshold, a crossing point between our star and the wider galaxy. When Voyager 1 crossed the heliopause in 2012, headlines around the world declared that humanity had entered interstellar space. It was a triumphant moment, but scientifically it was also deeply unsettling. The models were incomplete, the data was strange. The boundary was not behaving as expected. And then, from nearly 11 billion miles away, Voyager began to transmit something extraordinary. It detected sound. Not sound in the way we experience it on Earth. There is no air in interstellar space to carry vibrations to an ear. There is no atmosphere to ripple with pressure waves. But there is plasma. And plasma, though thin and nearly invisible, can oscillate. It can vibrate with energy, it can hum. Interstellar space is not empty. It is filled with a sparse mixture of ionized gas, mostly hydrogen, with traces of helium and heavier elements. The density is incredibly low, often just a few particles per cubic centimeter. On Earth, even the best laboratory vacuum contains billions of particles in the same volume. Yet in the vastness between stars, this thin plasma forms a continuous medium. Voyager carries an instrument called the Plasma Wave Subsystem. It was designed to detect fluctuations in electric fields caused by plasma oscillations. For years, inside the heliosphere, it recorded activity associated with the solar wind. But beyond the heliopause, something changed. In 2013, a coronal mass ejection erupted from the Sun. These events are massive expulsions of magnetized plasma that travel outward through the solar system like shockwaves in a pond. Months later, that disturbance reached Voyager 1's location in interstellar space. When the shockwave passed the spacecraft, it compressed the surrounding plasma. That compression caused the interstellar medium to oscillate. The plasma began to vibrate at a specific frequency, determined by its density. Voyager's instrument recorded those oscillations. When scientists converted the frequency into an audible range, they heard a rising tone, a sustained, eerie whistle. It was not a recording of air vibrating. It was a translation of plasma density into sound. The pitch corresponded directly to the number of charged particles surrounding the spacecraft. From that signal, researchers calculated the density of the local interstellar medium. It was significantly higher than the density inside the heliosheath. This confirmed what other instruments had implied. Voyager was no longer inside the sun's bubble. It was immersed in the galaxy. The sound of interstellar space was not silence. It was structure. This measurement was more than symbolic. Plasma density influences how cosmic rays propagate. It affects how magnetic fields behave. It shapes the interaction between stellar systems and the galaxy at large. For decades, astronomers had estimated these properties indirectly, through observations of distant stars and theoretical models. Now, for the first time, we had in situ measurements. Voyager revealed that the interstellar medium near our solar system is denser than many models predicted. That has consequences. A denser medium exerts more pressure on the heliosphere. It compresses the sun's magnetic bubble more tightly. It influences how far cosmic radiation penetrates inward toward the planets. In effect, Voyager's detection refined our understanding of the invisible environment surrounding every world we know. But density was only part of the story. The magnetic field beyond the Heliopause also held surprises. Before Voyager crossed the boundary, scientists expected a dramatic shift in magnetic field direction. The sun's magnetic field carried outward by the solar wind has a specific orientation shaped by the sun's rotation. The interstellar magnetic field, by contrast, is shaped by the galaxy's large-scale structure and local conditions. The expectation was that crossing the Heliopause would feel like stepping from one magnetic domain into another, with a clear change in direction. Yet when Voyager entered interstellar space, the magnetic field direction changed only slightly. This puzzled researchers. It suggested that the boundary between the heliosphere and interstellar space is more gradual and interconnected than a simple two-region model would imply. The magnetic fields appear to drape around the heliosphere, bending and interacting rather than colliding head-on. In fluid dynamics, when a solid object moves through a fluid, the fluid flows around it. Similarly, as the heliosphere moves through interstellar space, the galactic magnetic field appears to wrap around the sun's bubble. The transition is not a hard wall but a complex interface. Voyager's data indicated that the Heliopause may be layered. There may be regions where solar magnetic fields reconnect with interstellar fields. Magnetic reconnection is a process in which magnetic field lines break and reconnect, releasing energy. It occurs in solar flares and planetary magnetospheres. At the Heliopause, reconnection could create portals through which particles pass more easily. This would explain why some solar particles were still detected beyond the boundary, and why some galactic cosmic rays penetrated deep into the heliosheath. The edge of the solar system is not sealed. It leaks. The increase in galactic cosmic rays detected by Voyager was dramatic. These high-energy particles originate from distant supernovae and other energetic events in the Milky Way. Inside the heliosphere, the solar wind and magnetic field deflect many of them, reducing their intensity. Beyond the Heliopause, Voyager recorded a sustained rise in cosmic ray intensity. It was like stepping out from under a protective umbrella into a steady rain of radiation. This measurement has implications for future human exploration. If humanity ever sends crewed missions beyond the heliosphere, the radiation environment will be significantly harsher. Even within the solar system, understanding cosmic ray modulation is critical for assessing long-term exposure risks for astronauts traveling to Mars and beyond. Voyager's findings also contribute to astrophysics on a galactic scale. Cosmic rays play a role in heating interstellar gas, influencing star formation, and shaping the chemical evolution of galaxies. By measuring their intensity directly, Voyager provides calibration points for models of galactic dynamics. Another unexpected discovery was the persistence of solar influence beyond the Heliopause. Although Voyager entered interstellar space, it continued to detect effects from solar activity. Shock waves from coronal mass ejections propagated outward and disturbed the local interstellar plasma years later. This demonstrates that the sun's influence extends farther than the heliosphere itself. Energetic events at the sun can ripple outward into interstellar space, carrying information about solar cycles across immense distances. In a sense, Voyager revealed that our star is not isolated even at the boundary. The sun interacts continuously with its galactic environment. The heliosphere is a negotiation between internal pressure and external resistance. The local interstellar cloud through which the sun is currently traveling is itself part of a larger structure known as the local bubble, a region of hot, low-density gas likely carved out by ancient supernova explosions millions of years ago. Our solar system is moving through a dynamic and evolving galactic landscape. As the sun drifts through different regions over tens of thousands of years, The density and magnetic properties of the surrounding interstellar medium may change. If the solar system were to enter a denser cloud, the heliosphere could shrink. More cosmic radiation might reach the inner planets. Such variations may have influenced Earth's climate and biological history over geological timescales, though these connections remain areas of active research. Voyager's data does not provide definitive answers to those long-term questions, but it provides constraints. It anchors speculation in measurement. The spacecraft's instruments continue to record plasma oscillations, cosmic ray intensities, and magnetic field variations. Each data packet takes more than 20 hours to reach Earth. The signal is extraordinarily faint, requiring some of the most sensitive radio receivers ever built. Engineers must carefully manage the spacecraft's dwindling power supply, shutting down heaters and non-essential systems to keep the core instruments alive. Yet even as its systems age, Voyager remains a functioning scientific outpost in interstellar space. It is easy to romanticize this achievement, to see it as a symbolic crossing into the unknown, but its significance is concrete. It transformed interstellar space from an abstraction into an environment with measurable properties. It provided empirical evidence that refines plasma physics, magnetohydrodynamics, and cosmic ray theory. It also reframed our place in the galaxy. For centuries, humanity has expanded its horizon. From continents to oceans, from the moon to the outer planets, each expansion has forced a recalibration of perspective. The Heliopause is not just a boundary in space, it is a boundary in comprehension. Before Voyager, the edge of the solar system was a theoretical construct derived from equations. After Voyager, it is a mapped frontier with coordinates, densities, field strengths, and particle spectra. And still, the spacecraft moves outward. With every passing year, it penetrates deeper into interstellar space. The density of plasma slowly changes. The magnetic field orientation shifts gradually as Voyager samples new regions of the local cloud. Subtle fluctuations hint at larger structures beyond our immediate neighborhood. Somewhere ahead lies the boundary between the local interstellar cloud and whatever region comes next. That crossing, if Voyager survives long enough to detect it, will provide further insight into the patchwork nature of our galaxy. The Milky Way is not uniform. It is structured into spiral arms, molecular clouds, superbubbles, and filaments shaped by gravity and magnetic forces. Our sun's journey through this environment is slow but continuous. Voyager is the first emissary to scout the immediate terrain. When historians of science look back on this era, they may see Voyager's crossing of the Heliopause as the moment when humanity first extended its instruments beyond the influence of its home star. It is a milestone comparable to the first orbit around Earth or the first footprint on the Moon. But unlike those events, it happened in silence. No live broadcast, no cheering crowds, just a faint signal decoded by scientists and engineers who understood what the data meant. What Voyager detected at the edge of our solar system was not a dramatic barrier or a sudden plunge into darkness. It was a subtle but profound transition, a shift in particle populations, a change in plasma density, a new magnetic regime, the hum of interstellar space itself. In that hum, we heard confirmation that the galaxy is not distant. It presses against us, it surrounds us. And now, through a machine built nearly half a century ago, we are listening to it directly. The edge of the solar system is no longer a concept. It is a measured reality. And beyond it, the vast structure of the Milky Way waits, not silent, but quietly resonant with energy.